When we finished up Chapter 2 last week, we had determined that the atom has a tiny nucleus which contains the protons and neutrons, and the electrons are just sort of flying around out there somewhere. And that everything in between the electrons and the nucleus was nothing but empty space. So atoms are about 99.99999% nothing. As it turns out, the electrons are the most important part of the atom when it comes to chemistry, because they're on the outside of the atom. Contrary to what your parents tried to teach you as you were growing up, it's not what's on the inside that counts. For atoms, it's how they look. It's what's on the outside that matters. Because when two atoms come together, it's those electrons on the outside that actually interact with each other. So in Chapter 11, we're going to spend most of our time understanding how the electrons are organized around the atom. It turns out they're not just haphazardly flying around the nucleus. They are organized in very specific ways, which is dictated by something called quantum mechanics. So we'll talk a little bit about that. So by the end of Chapter 11, you should have a very good idea of the electronic structure of the atom and how that dictates the properties of an atom. And that we can use that information when we go on to Chapter 3 next week and talk about what kind of chemical reactions elements undergo. Their chemical reactions are essentially dictated by how their electrons are organized. So that's what we want to focus on in Chapter 11. When we finished up Chapter 2, we had gotten to the point of Rutherford's model of the atom, which basically has a tiny positively charged nucleus in the center, and the electrons are just sort of flying around outside. They didn't really know exactly where the electrons were, but they were flitting around somewhere out here, and there was nothing but empty space in between the nucleus and the electrons. In Chapter 11, we are going to focus entirely on what the electrons are doing. Because as I've said to you several times already, it's not what's inside that counts, it's what's on the outside. And of course, the electrons are on the outside of the atom, and therefore it's the electrons that determine the chemical properties. So scientists began to study these electrons to see how they were organized in the atom. They're not just flying around haphazardly. They are very thoroughly structured in where they exist in the atom. In order to study the atom, we're going to put energy into the atom and cause some changes to happen to those electrons. In a normal situation, the electrons are as close to the nucleus as they can get because opposite charges attract each other. This is referred to as the ground state of the atom. It's sort of like if you drop a ball, it falls to the ground. So the electron, if you drop an electron into the atom, it falls as close as it can get to the nucleus. You might be wondering, well, why doesn't it go even closer? And the answer to that question will come up a little later in the chapter when we talk about quantum mechanics. So if we put energy into an atom, it will kick the electron up away from the nucleus. And this is called the excited state. The electron now has greater potential energy. It's no different than if you took a ball and you threw it up in the air. If you throw the ball up in the air, it now has more energy up there than it had down below because of gravity. Gravity wants to pull the ball down. The nucleus wants to pull the electrons down. There's actually 3 different ways that you can excite an electron. One way is you can heat it. We'll be doing that in experiment number 6 in the lab. We're going to be heating different elements, and that's going to cause the electrons to jump to the excited state. You can pass electricity through an atom. And we did that in the last chapter. If you remember our cathode ray tube, that's essentially what we were doing. And the third way we can excite an electron is using something called electromagnetic radiation. Whichever of these 3 ways you excite the electron, the net result is always the same. Once the electron goes up to the excited state, it has to fall back down to the ground state. If you throw a ball up in the air, it's going to fall back down. That's just the way things work. The interesting thing about the atoms is when the electron goes back to the ground state, the energy is always released in the same way, and that is electromagnetic radiation. Every time one electron falls back to the ground state, we release one photon of electromagnetic radiation. A photon is like a piece or a particle of electromagnetic radiation. The different types of electromagnetic radiation are defined by their wavelength. It's simply the distance measured between the peak of two consecutive waves. So the wavelengths can be small, they can be medium size, they can be large. Depending on the wavelength, tells us what kind of electromagnetic radiation we have and how much energy they have. This represents what we call the electromagnetic spectrum. It shows the various types of electromagnetic radiation from radio waves all the way up to gamma rays. As I mentioned a moment ago, the difference between the various types of electromagnetic radiation is their wavelength. On the long wavelength end of the spectrum, we have radio and television waves. Their wavelengths can be as great as a kilometer across. So one of these waves would stretch across the entire college campus. Gamma rays can be as small as 10 to the minus 12 meters. That's a trillionth of a meter. So the difference between a radio wave and a gamma wave can be 10 to the 15th power. That's 1,000 trillion times difference. It is important that you realize that the energy increases as you go from radio to gamma rays, but the wavelength decreases. Wavelength and energy are inversely proportional. That is something you will want to remember when you're taking quizzes and exams. You will need to know the 7 types of electromagnetic radiation, and you'll need to know them in order of both energy and wavelength. So in order of increasing energy, it's radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. In terms of wavelength, it's the opposite. The wavelength increases as you go from gamma back to radio waves. Now, in the middle of all of this, we have visible light, and we've sort of separated that by itself because that's our favorite kind of electromagnetic radiation, for the simple reason is that we can see it. Our eyes can only detect this narrow little band of electromagnetic radiation. The waves have to be just the right distance apart for our eyes to detect them. Visible light also comes in 7 different types, which we commonly refer to as colors. We have red, orange, yellow, green, blue, indigo, and violet, and the acronym Roy G. Biv is commonly used to remember that. We could basically just write that in reverse here. There's Roy G. Biv, and that tells us the order of the colors of the rainbow, from red, which has the least energy but the longest wavelength, up to violet, which has the most energy but the shortest wavelength. When studying the behavior of the electrons, I like to use an analogy which I call the energy hill. This is basically a potential energy hill. Everything in the universe essentially sits on a potential energy hill, and it's the nature of everything to want to get to the bottom of a hill. If you set a ball at the top of a hill and let it go, it's going to roll down to the bottom. If you set a ball at the bottom, it is not going to roll up to the top. So it's the nature of things to want to get to the lowest position, that is, the lowest amount of energy. The electron in the ground state is essentially at the bottom of our energy hill. Now, if we put energy into this electron, let's suppose we give it a little bit of energy. We heat it or pass some electricity through it. The electron is going to move up the hill a ways, but then it's immediately going to fall back down. It's just like if you kicked a ball up the hill, it's going to roll right back down again. But in the case of the electron, it's going to emit a photon of electromagnetic radiation. Just for example, let's suppose that this small drop in distance produced a rather low energy photon, which is red light. We could kick the electron again, but this time let's kick it farther up the hill. When it rolls back down, of course, another photon will be emitted, and let's suppose this time, because the distance was greater, we now get a photon of green light. If we give it another kick, we really kick it up the hill, when it falls that greater distance down, we should get an even more energetic photon, and this time we'll get a photon of blue light. And you may notice that I have shortened the wavelength as we go along. Photons of blue light have just about half the wavelength of photons of red light, which means they have about twice the energy. Now suppose I wanted to make orange light come out of my atom. Logically, since orange falls between red and green, if I were to kick the electron farther than I did for the red photon, but not as far as I did for the green photon, I might expect to get orange light. If I wanted yellow, I might kick it here. If I wanted violet, I'd kick it up here. Logically, we should be able to produce all the colors of the rainbow just by varying how much energy we put into the electron and how far we kicked it. But what scientists found is you don't get orange light. If you kick the electron with this much energy, you get red light. If you kick it with this much energy, you get green light. If you kick it with this much energy, you get nothing. This much energy, nothing again. If you kick it with this much, nothing. For some reason, you could only get very specific colors of light to come out of this atom. And scientists, of course, were wondering, why is that the case? I mean, looking at our energy hill model here, it seems like we should be able to kick the electron up any distance we want and thus make any particular color of light that we want. But for some yet unknown reason, that simply wasn't possible. An atom would only produce very particular colors of light, and they're not always the same. A different atom might produce yellow, orange, and violet. It all depends on the element. Back in the early 1800s, scientists studied the light being emitted by various elements. They would heat the elements up or pass electricity through them, and they would observe the colors of light that were being given off. They would pass the light through a prism and separate them into their various colors, and they found, interestingly enough, that each element that they tested gave a different set of colors. Sodium, for example, just gives a couple of yellow colors. If you've ever been in a parking lot and you've seen those really gaudy yellow overhead lamps, those lights have sodium in them, and that's why they look so yellow. Neon has a lot of lines up in the red and orange end of the spectrum. A true neon light is red-orange in color. When you see different colored lights, the blues, the greens, the yellows and such, they're not really neon lights. They may call them a neon light, but it's not neon that's making it. It's some other element they put in there to make those different colors. So, of course, scientists were wondering, why is it that these atoms produced only these very specific colors? Because back in the early 1800s, all we knew about atoms was that they're little indivisible balls. No one had yet discovered electrons, protons, neutrons, or anything like that. So scientists really had no idea why elements could only produce particular colors and why each element produced different colors than the other ones. To explain these observations, scientists needed to come up with a new model for the atom, and the model I like to use I call the energy staircase. We imagine that the electron is not sitting on a smooth hill, but rather it's on a staircase. So if you put energy into an electron, the least you can do is to kick the electron up one step. When the electron falls back down that step, we get our photon of red light. Our second possibility is we could kick the electron up 2 steps, and when it falls back down, now we get our photon of green light. If we kick it all the way to the third step and it falls back down, now we get our photon of blue light. Well, what would we have to do to get a photon of orange light? We would have to go somewhere between the first step and the second step. And that's simply not possible. If we were on campus, and I'm sure most of you have been at one time or another, if you wanted to come up to our chemistry lab on the third floor, you would have to come up several flights of stairs. Now, most students come up the stairs one step at a time. But some of us, myself included, if we're in a hurry, we might come up the stairs 2 steps at a time. But have you ever tried to come up the stairs 1.5 steps at a time? If you did, you probably fall on your face and break your nose. It's not possible to go up the stairs 1.5 steps at a time. It's either 1 or 2 or 3, but nothing in between. Again, scientists didn't know why atoms behaved this way, but it appeared that in the atom there were these sort of staircases or steps that the electrons could travel, and they could go only a whole number of steps. They could never go anywhere in between. In 1913, based on these observations, Niels Bohr came up with a new model of the atom. It's sometimes called the planetary model because it sort of looks like the solar system. We've got the sun here, and then we've got Mercury and Venus and Earth, and so on and so forth, with the electrons circling around the nucleus in these various orbits, which are commonly referred to as energy levels. So Bohr came up with an idea that the electrons in an atom were restricted to these very specific distances. They could be here, here, or here, but nowhere in between. Now, one of the downsides of Bohr's theory was he had no explanation as to why the electrons were restricted. Why couldn't they be here? If this were truly the solar system, could something orbit the sun between Venus and Earth? Absolutely. That would be no problem at all. You could have an object orbiting the sun at any distance from the sun. There is no limits to how far they could be. But for some reason in the atom, that's the way the atom was designed. So if we look at the atom, we've got our electrons in the ground state. They can jump up a level to an excited state. They could even jump up higher levels, but they always have to jump to a very specific distance. And when they fall back down, of course, they release that photon. If we were to kick an electron up, say, 4 levels here, from level 2 all the way to level 6 in the atom, the electron could fall all the way down from level 6 to 2. That's a very far distance, and now we get a photon with a lot of energy. If an electron only jumped up to level 5 and came back down, now it's falling a shorter distance, perhaps we get a blue photon. Jumping only 2 levels and coming back down, we get green, and only 1 level gives us red. So the Bohr model of the atom did a pretty nice job of describing what was going on in the atom, not so much describing why it was that case. But Niels Bohr was able to come up with even with a mathematical equation that would calculate the energy that each photon would have depending on which 2 levels it fell between. You could have an electron fall from level 8 to level 3, and his mathematical equations could calculate what the energy would be of that particular photon. When you fall down to level 3 from a higher level, the energy is less, and so you usually get things in the infrared realm. But unfortunately, the Bohr model didn't tell us why atoms might be designed the way they were. So why do energy levels actually exist? Let's go back a ways and think about light first. Democritus, as you may recall back in chapter 2, suggested that matter consisted of individual particles. He had the same idea about light. He thought that light was also some kind of particle, just like matter. In 1000 AD or CE, Ibn al-Haytham, who was an Arab scientist, also had the idea that light was a particle. This seemed to be a pretty popular idea. However, by the 1700s, some scientists began to wonder if light was actually a wave. A lot of the behavior of light seemed to be only explainable if we looked at light as a wave rather than a particle. So for a couple of hundred years, there was a lot of debate about this. Isaac Newton, very famous physicist, he thought light was a particle. He called them corpuscles. In the 1850s, most people were beginning to come around to the idea that light was actually a wave. Foucault was convinced of it and had lots of good experimental evidence to support the idea that light was a wave. So from the mid-1800s on, people were pretty well convinced that light was a wave. But then, in 1905, Albert Einstein, in the paper that won him his Nobel Prize in Physics, figured out that light could actually be both. Sometimes light acted like a particle, sometimes it acted like a wave. Nobody actually knew for sure. In fact, no one still knows for sure. We sometimes refer to light now as a wavicle because sometimes it seems like it's a wave and sometimes it seems like it's a particle. A similar type of question was asked, of course, about the electron. Back in all through the 1800s, people debated whether electrons were particles or waves. We talked in Chapter 2 about all the different experiments that were done with the cathode ray tube and such to try to pin down the nature of the electron. In 1897, J.J. Thomson did his experiments with the cathode ray tube and figured out electrons were definitely particles. Or were they? In 1924, a French physicist, Louis de Broglie, came up with a novel idea. He said, well, you know what? If light can be both a wave and a particle, is it possible that electrons and other particles could do the same? And he came up with a wave equation, and he predicted that electrons could behave as waves under certain conditions. And it was only about 8 years after that that scientists actually did experiments, and they were able to prove conclusively that electrons sometimes acted like waves rather than particles. It's called the wave-particle duality. And again, just like light, we're not exactly sure what an electron is. Sometimes it acts like it's a wave, sometimes it acts like it's a particle. All of these ideas came together in the 1920s with the concept of quantum mechanics. It was basically a new way of looking at the atom and, in fact, of the entire universe. First of all, quantum mechanics assumes that electrons can behave like waves rather than particles, thanks to that idea that particles can have both the characteristics of waves and particles. It assumes that energy comes in specific amounts or specific quantities, which are called quanta. So the single smallest unit of energy is called a quantum of energy, and the plural of that is quanta. So those ideas that Democritus had back in 500 BCE that matter consisted of indivisible particles, apparently that idea also applies to energy, something that people did not really realize. And the reason they didn't realize it is because the individual quanta of energy are incredibly tiny. They were so small, they were virtually unmeasurable until we delved into something as tiny as atoms. A quantum of electromagnetic radiation, as we said before, is referred to as a photon. So when it's electromagnetic radiation, it has its own special name. Quantum mechanics merged what we refer to as classical physics. That's the physical laws of people like Isaac Newton. And what they did is they merged these ideas, equations of classical physics, or sometimes called mechanics, with this wave idea, and that's what gave rise to quantum mechanics. So back to our original question, why are there energy levels? Let's take a look at a wave on a string. I don't know about you guys, but when I was a kid, I used to do this sometimes. I'd take my mother's vacuum cleaner cord when it was plugged in, and I would start whipping it up and down because it was pretty fun to make waves. Or you could take a jump rope and do the same thing. An electron is considered to be like this. It's simply almost like a wave on a string. This is known as a standing wave because the wave isn't really going anywhere. It is staying between the tree and this person. You'll notice that there are 1, 2, 3 peaks along this wave. If we begin to move the rope faster, it might increase. Now we've got 1, 2, 3, 4 peaks. If you do this at home, or if you've ever done this, the one thing you will notice is the number of peaks is always a whole number. The wave must start at one end and must finish at the other end. It can't just end up here. It wouldn't be connected to the tree. So in order for the wave to maintain its integrity, there has to be a whole number of wavelengths. For example, in this one here, we have a nice whole number of waves around this atom, so they all connect with each other. So there's 1, 2, 3, 4 wavelengths. In this example over here, the number of wavelengths is not a whole number, so the two ends don't actually connect. That would be like the end of a jump rope not being in your hand, but being above your hand. If that were the case, then the rope would simply fall to the ground and collapse, and that's exactly what would happen to the waves here. So quantum mechanics said the only way these electron waves can maintain their integrity is there has to be a whole number of them. Let's take a moment here. I found an interesting little video on YouTube that shows the importance of having these whole numbers of waves. As I said before, the smallest number of wavelengths you can have is 1. So if you move your rope or your spring up slowly, you can make 1 wavelength. As you can see, the wave has to begin at one person's hand and has to end at the other. If it didn't go exactly between their two hands, one of them wouldn't be holding it, and the wave would simply collapse. Now, if we begin to move the spring faster, it suddenly jumps from 1 wavelength to 2. You notice we never get anything in between. You can't have 1.5 wavelengths or 1 3/4. It always has to be a whole number, so that once again the spring starts at one person's hand and it ends at the other. In 1926, a German mathematician, Erwin Schrödinger, came up with what's known as the Schrödinger equation, and it gave us a really detailed description of the atom. From that, we were able to make a lot of predictions about atomic structure. So what exactly did Schrödinger's work in quantum mechanics tell us about atoms? The first thing that his equations predict is that atoms should have energy levels, and indeed they do. Bohr had realized that, about 13 years earlier, but Schrödinger's mathematical equations explained that that had to be the case. According to quantum mechanics, energy levels are simply numbered from 1 on. And there are an infinite number of energy levels in every atom. That's an important thing to remember. Even though we don't use all of those energy levels, that's way more than we would need. The largest atom we currently have only holds 118 electrons. The first 7 energy levels are more than sufficient to hold those electrons, so at present there is no atom large enough that needs more than the first 7 levels, but you do want to remember that there are an infinite number of levels present. The other thing that Schrödinger's equations tell us is how to determine the number of electrons that each level will hold. As you might guess, as we go out from the atom to ever larger levels, they can hold more electrons. The first level, which is close to the nucleus, isn't very large. As we go out, the levels become larger and larger. So we can calculate the number of electrons using this calculation, 2n squared, where n is just the level number. So in the first energy level, 2 times 1 squared is 2. The first level only holds 2 electrons. The second level, we have 2 times 2 squared, which is 2 times 4, or 8. 2 times 3 squared gives us 18 electrons in the third level. 2 times 4 squared is 32, and 2 times 5 squared is 50. Now at this point, if we were in class, I always ask the students the same question. Could you predict the number of electrons that would be in energy level number 6 without using the 2n squared calculation? You should be able to look at this series of numbers and nothing else and be able to make a prediction of what the number of electrons would be in energy level number 6. So you can pause the video for as long as you'd like and give that some thought, and eventually someone always realizes what the pattern is. All right, if you've thought about it now, let's see if anybody figured it out. The answer is there will be 72 electrons in this next level. And we can figure that out if you look at the changes between levels. Between level 1 and 2, we went up by 6, and then we went up by 10, and then 14, and then 18. Every new level, the increase is 4 larger than the previous one. So if we went 6, 10, 14, 18, the next jump ought to be 22, and 2 times 6 squared is indeed 72. If we went up by 22 here, we should go up by 26 in the next one, and of course 2 times 7 squared is 98, and of course 2 times infinity squared is infinity. As I like to keep saying, when it comes to atoms, it's what's on the outside that counts. So we're interested in finding out what electrons are on the outermost level in the atom. One way to figure that out is simply to start putting the electrons in the atoms and see where we end up. So we'll take a look at this point just at the first 4 energy levels in an atom, and we'll begin to put the electrons in one element at a time. We'll begin with hydrogen. Hydrogen is element number 1. It has 1 electron. Now there's an unbreakable rule when it comes to placing the electrons in the atom, and that is this. You must always put the electron at the closest available spot to the nucleus. So for example, we could not put this first electron in level 2. It has to fall down into level 1. Now this is going to become important in a little while, because you're going to think I'm violating that rule, but I'm going to show you I'm really not. We move on. Element number 2 is helium. There's still room in energy level number 1 for a second electron, and so we put it there. At this point, we've now filled energy level number 1. The second energy level can hold 8 electrons, as you recall. So let's move on to lithium. We'll put lithium's third electron in level 2, and then we'll continue on across the second period. For beryllium, we'll put that electron also in level 2. For boron and carbon, nitrogen, oxygen, and fluorine, and finally neon. By the time we've made it across the second period on the periodic table, we have now put 8 electrons in energy level number 2, and that level is now full. That means when we go to period number 3, with sodium, we're going to have to start filling energy level number 3. And as we go across the third period, we will continue to do that. So magnesium's 12th electron will go in level 3, and then across we'll go with aluminum, and then silicon, phosphorus, sulfur, chlorine, and finally argon. So by the time we've made it across the third period, we now have 18 electrons in our atom, 2 in the first level, 6 in the second level, 8 in the second level, and 8 in the third level. Now the question is, where should we put electron number 19? We're about to move on to potassium. Remember my rule, and the rule was that you must always place the electron to the closest available spot in the atom. And that would appear to be level number 3. The third level holds 18 electrons. We've only got 8 in there. Should be room for 10 more. However, there's a pattern that you may have observed when we've been going through and filling up these elements. As we go through each energy level in the atom, we're also going through a period in the periodic table. We filled hydrogen and helium in energy level number 1, which also comprises period number 1 on the periodic table. When we filled elements lithium across to neon and completed the second period, all of those 8 electrons went in the second energy level. We moved on to sodium in energy level period number 3, and we began to fill energy level number 3. So sodium across to argon, we went across the third period, we filled part at least of the third energy level. The trend then that we notice is every time we started a new period on the table, we started a new level in the atom. When we began period number 1, we began filling energy level 1. When we hit lithium and began to fill period number 2, we went to energy level number 2. When we started with sodium in period number 3, we went to energy level number 3. So the question is, when we go to energy level number 4, or period number 4 with potassium, should we follow that trend and go to the 4th energy level, or do we need to obey the unbreakable rule and put that 19th electron in energy level number 3, since there's still space available? Surprisingly, it turns out that that 19th electron in potassium actually goes into energy level number 4. Now this may seem like we're violating our unbreakable rule, but it turns out the structure of the atom is a little more complicated than we thought. We've already decided that the atom is divided into energy levels, and the number of electrons in each energy level can be determined by this equation 2n squared. However, it turns out that the energy levels themselves can be divided into even smaller units, which are called subshells. Each energy level in the atom has one or more subshells. If you think about it, the goal in an atom is to keep the electrons away from each other. Electrons don't like each other. So the first thing we did was we separated them into individual levels, but still there can be a lot of electrons in one level. By dividing them into subshells, we can isolate them even further from each other. And the existence of subshells was predicted by the mathematical equations of Schrödinger. The rule is very simple. The number of subshells in an atom is the same as its energy level. So in energy level number 1 in any atom, there'll be one subshell. That first subshell is known as an S subshell, and S subshells always hold 2 electrons, so they're pretty small. If we go to energy level number 2, there will be 2 subshells. And one thing that makes this convenient is that the subshells always repeat. So if there's an S in level 1, there'll be an S in level 2, but we'll add to that a P subshell. Since the total number of electrons in the level have to add up to 8, if the S holds 2, then the P would have to hold 6. If we go to level 3, we'll have 3 subshells. The first one, of course, will be an S subshell. We'll also have that P subshell, but we have to add a third subshell, and that third subshell will be a D subshell. You may have noticed, interestingly enough, that the size of the subshells is increasing by increments of 4. That same thing we noticed over here earlier, how the energy levels kept getting larger by an additional 4 electrons every time, and that's because the subshells are increasing in size in increments of 4. If we go to level 4 with 4 subshells, there'll be an S and a P and a D, and now we will add an F subshell, and that F subshell, of course, will hold 14. If you add 14, 10, 6, and 2 together, of course, we get a total of 32. So in each of the energy levels, we divide the level into subshells, and the number of subshells will be whatever the energy level is. So in energy level 7, there will be 7 subshells. Now, after level 4, we continue alphabetically. So in level 5, we'll add a G subshell, which holds 18. In level 6, there'll be an H subshell that holds 22, and that process will continue to infinity. But as I said earlier, there's no atom in existence yet that needs more than 7 energy levels. That is more than enough to hold the maximum of 118 electrons that the largest currently known atom contains. So how big are atoms? Well, they're very tiny. Okay, atoms are extremely small, which is why it was very difficult for people to find atoms. Another question, how many energy levels are there in an atom? And as we said before, it's infinite. So a very good question comes up, how do you squeeze an infinite number of energy levels into a very tiny space like an atom? Turns out that our picture of the atom wasn't entirely accurate when we drew our atomic staircase earlier. The only way you can fit an infinite number of levels in a tiny little space like an atom is to decrease the spacing between the levels. So the levels get closer and closer together. By the time we get out to energy level number infinity, we're only about right here. The atom never gets much bigger than this, about 200 trillionths of a meter in size, which is very, very small. That's like 0.2 billionths of a meter. So it's very important to recognize that the energy levels, the first level from 1 to 2 is big. That's about 75% of the entire size of the atom in that one step. The second step is about 20%, and then they get progressively smaller as you go along. So now we know 2 things about our atoms. Number 1, the energy levels are divided into subshells, and number 2, the energy levels get closer and closer together as you move away from the nucleus. Let's take our atomic staircase then and add to that this new idea of subshells. So we'll lay the subshells next to each of these energy levels. What you can see then, of course, is that an energy level is not just a thin little region. It's actually divided into these subshells. The farther out we go, the more subshells there are. So there's a nice big gap between energy level number 1 and energy level number 2. Between level 2 and 3, the gap becomes much smaller. And of course, it's obvious that as the levels begin to move more and more horizontally, there's going to be some overlap. We can see that the bottom of level 4, the 4s subshell, is actually closer to the nucleus than the top of level 3. When we were doing potassium, we finished up argon. We had done 2 in the 1s, we had put 8 electrons in level 2, and we had put 8 electrons in level 3 for a total of 18. Our question was, where should we put electron number 19? And the debate was, should we put it in the still open part of energy level 3, or should we jump up and begin energy level number 4, like that pattern we observed on the periodic table? It turns out that we went to level 4 and we didn't break the unbreakable rule, because the 4s subshell is currently the closest available spot to the nucleus. It is closer than the 3d subshell. Now, after we finish filling the 4s, we'll go back and we will wrap up energy level number 3. But from here on out, we're going to be going back and forth between the various levels. Level 5 is going to even be more overlapped with level 4, and level 6 even worse than that. So a diagram like this is not going to be helpful. We need an easier way from potassium forward to figure out where to put the electrons. And to do that, we're going to use the periodic table. If you take a look at the periodic table, you'll notice that it's essentially constructed of blocks. There's a tall, thin block over on the left side. There's pretty much a square shape over on the right. There's a rectangular block in the center and a long rectangular block at the bottom. You may be wondering also why we have this gap from, say, 57 to 72 and 89 to 84. The periodic table would actually look like this if we put it in its true form. The way we got from this table to the one you commonly see is we essentially cut out these elements in the middle and we drop them down below, and then we simply slid the two sides together. You're probably thinking, ooh, there must have been some scientific and technical reason for that, and unfortunately that wasn't the case. The reason's simple. This version fits on the wall better. This long version of the periodic table simply takes up a lot of wall space, so chemists found it easier just to remove this block of elements and put it down below, because these elements are rarely involved in chemical reactions. They're rather uncommon elements. They're actually referred to as the rare earth elements because they are fairly rare. Most chemists never deal with chemical reactions using these elements, so we don't really mind dropping them off down to the bottom a little bit out of the way. And we focus on these three blocks of elements instead. You probably noticed earlier that there were letters and numbers in each of these little segments of the periodic table. This block is 2 elements across, and since an s subshell holds 2 electrons, we call this the s block of elements. This one, of course, being 6 elements across, is referred to as the p block. This center block of elements is 10 across, thus the d block, and the block down below that is 14 elements across, we call that the f block. When the periodic table was created, nobody knew why the elements seemed to fall into these blocks. We know now, of course, once quantum mechanics and Schrodinger's equations came along, that when we enter the S, the P, the D, or the F block, we're also entering that same subshell in the atom. For example, when you hit the element indium here, element number 49, you are beginning to fill the 5p subshell in the atom. So we're in energy level number 5 and we're filling the p subshell. If you hit francium, we're now filling the s subshell in energy level number 7. We're going to find that this periodic table is a very useful guide in terms of assigning each electron to its location in the atom. And that's the next thing we want to work on. We want to try to be able to show where each of the electrons is located in an atom, again, with our major goal to determine which of those are on the outside. We want to know which electrons are in the outermost energy level, because it's what's on the outside that counts. To determine which electrons are indeed on the outside of the atom, we're going to write out what's known as the electronic configuration of the elements, which is basically just a list of the location of each electron in the atom, both the energy level and the subshell in which that electron is found. Let's begin with the beginning. with hydrogen. You can see that hydrogen is in the 1s block of the periodic table, which means, of course, we're going to be starting by filling the 1s subshell. Hydrogen has only one electron, so its electronic configuration is simply 1s1. The first one tells us it's energy level 1. The S says we're filling subshell S, and the superscripted 1 tells us there is one electron. So one electron in the S subshell of energy level number 1. That's where our hydrogen's electron is found. If we jump over to helium, helium is also in the 1s. Now you might be thinking, wait a minute, it looks like it's in the p block. Well, it sits in the p block, but it's not really a p element. Energy level number 1 doesn't have a p subshell. In level number 1, there's only an s. The p subshell first appears in energy level number 2. The d first appears in level 3. The f first appears in level 4. From an electron standpoint, it would make sense to put helium right over here next to hydrogen. Do you have any idea why we don't do that? The answer is very simple. Helium is nothing like the other elements in group 2 on the periodic table. Helium's properties are actually very much like the other elements over here in group 18. When the periodic table was designed, the number one goal was to group elements by properties. Back in the days of Mendeleev, they had no idea that elements even had electrons in them, or energy levels, or whatever. The only thing they knew is that elements had particular properties, and it would make no sense to put helium over here. But even though helium is sitting on top of the p block, it's really part of the s subshell. So helium's electronic configuration will be 1s2. It has 2 electrons in the s block of energy level number 1. Let's jump down now to the second period and take a look at lithium. Lithium has 3 electrons. One convenient thing about electronic configurations is that whatever an element has, the next element is going to have all of that and simply one more electron. So lithium is going to have everything that helium had plus one more. To get to lithium, we have to start here. We have to go through the 1s subshell and then come back to the 2s. So 2 electrons in the 1s, and that third and final electron is in the 2s subshell. If you think about it, that means that lithium really has 1 electron on the outside because these 2 electrons are on the inside. That's something hydrogen and lithium have in common. They each have 1 electron on the outside. If we move on to beryllium with 4 electrons, it's going to have everything lithium had but 1 more. So beryllium has 2 electrons in the 1s and 2 electrons in the 2s. When we jump over to boron, we're now going to enter the 2p block of the elements. So boron is going to add a 2p1. It's got 1s2, and then 2s2, and 2p1. As we continue across the second period, we're just going to continue filling up that 2p subshell. So carbon, it will go to 2p2. Nitrogen will jump to 2p3, oxygen to 2p4, fluorine to 2p5, and finally we get to neon, which will end with 2p6. By the time we get to neon, we have now completely filled energy level number 2. To go to sodium, we're going to go back and begin the third period on the periodic table, and we're going to open up the third energy level. Sodium is in the 3s block of elements. So sodium has everything that neon had, plus we have to add that 11th electron, which is in the 3s subshell. Now, electronic configurations can get pretty long. If we get down to, say, element number 112, that's going to be a lot of electrons to write down. So chemists came up with a shortcut. We call it the shorthand electronic configuration. If you take a look at the electronic configuration of sodium, you'll notice that the first three parts of it are essentially neon. The 1s, 2s, and 2p, that's everything that neon had. So we can simply lump all those together and just write neon. It's okay to do that. We don't really care that much about the details in level 1 and level 2 in sodium because they're not on the outside. The electrons in the inner levels have very little impact on the properties of an atom. The chemical properties are almost entirely determined by what's in the outermost level. So all we really are interested in with sodium is what's on the outside. So it's basically everything neon's got, and then it's got that one electron on the outside. Let's go ahead now and work through a few examples just to show you how you'll be doing this on your worksheet. We'll start out with phosphorus, something with not so many electrons. Phosphorus is in the third period. With the shorthand electronic configurations, we always start with whichever noble gas comes at the end of the preceding period. So with phosphorus element 15, we'll want to begin with neon element 10, and that will take care of 10 of our 15 electrons. After neon, on the way to phosphorus, we next enter the 3s block of elements, so we'll pick up those 2 electrons from the 3s, and then finally, to get to phosphorus, it's 1, 2, 3 elements into the p block, and it will end then with 3p3. A good way to check your work, especially when you're using larger atoms, is to count the electrons. When your electronic configuration is done, it should have 15, no more and no less. We have 10 for neon, plus 2 and 3, that's 15 electrons. That's a good sign that you've probably done it correctly. Next, we'll take a look at ruthenium. We'll drop down into the D block and see how we handle the D block elements. Since ruthenium is element 44, we'll want to begin with krypton. That's the preceding noble gas, and that will take care of 36 of our 44 electrons. After krypton, we go down to rubidium and strontium, which make up the 5s block of elements. So we'll add our 5s2, and then we enter the 4d block. It's important to remember that the D blocks are numbered 1 lower than the S and the P block, and that's because, as we learned earlier on, we don't fill everything in order. Remember with potassium how we jumped up to the 4s, but then we had to go back later and finish the 3d. So whenever you're doing an electronic configuration, always remember that the Ds are being filled 1 level later, and that's why they're numbered 1 lower. So after strontium, we enter the 4d block, and we have 1, 2, 3, 4, 5, 6. Ruthenium is the 6th element over, which means we'll end with 4d6. If we check our math, we have 36 plus 2 is 38, 6 more makes 44, and ruthenium is element 44. Next, let's jump down in and look at an F block element. We'll do gadolinium, element number 64. Now, sometimes people think, oh, if I'm starting down here, I'll go back to radon. That's the closest noble gas, but it's not. 86 doesn't come before 64. Remember that these elements in the F block are actually inserted into the table here. So the closest noble gas before number 64 would have to be xenon, element number 54. So that's where we will get started. Then we enter the 6s block and pick up cesium and barium, which gives us 6s2. Now we enter the 5d block, but we're only going to go in 1 element because notice there's a gap here. After 57, we have to drop down. So we'll only pick up the first member of the 5d, which will give us our 5d1. Then we'll drop down into the F block in the 4F, and we'll pick up 1, 2, 3, 4, 5, 6, 7 elements or 7 electrons in the 4F, which means we'll end with 4F7. Checking our math, we've got 54, 2 more is 56, this one makes 57, and 7 more adds up to 64, which is the number of electrons that an atom of gadolinium should have. Now we'll move on to platinum. We'll pick an element in the D block that's after some of the F block elements, and that'll add a new little wrinkle here. So platinum is element number 78. So again, xenon will be the closest noble gas before that. After xenon, like gadolinium, we'll pick up the 6s block and pick up those 2 electrons. We'll then go to lanthanum and get our 5d1 as we did before. Now we'll jump down to the 4F, but this time we're going to go all the way through the 4F in order to get to platinum. So we'll add all 14 of the members of the 4F block. Now the tricky part. We're going back into the 5D block. A lot of students want to write down 5D again here. You don't want to do that. There's only one 5D subshell in the atom. We put 1 electron in it initially, and now we're simply going to add some more. We need to add another 1, 2, 3, 4, 5, 6, 7 more electrons to that 5D subshell, and that's going to increase it to 5D8. So don't write a subshell twice, simply combine them together. Again, if we check our math, we have 54, 56, 64, 74, and 78, and that, of course, is the atomic number of platinum. And now for the final one, let's pick an element that's actually exists but hasn't quite made it onto this older periodic table, flerovium, which is element number 114. At this point, the most current periodic tables have elements all the way out to 118. This one just happens to be a few years older. So flerovium, element 114, will have to begin with radon, which will pick up our first 86 electrons. We'll then go down here to the 7s block and pick up those 2 for 7s2. We go to actinium and pick up just that 1 member of the 6d block for 6d1 before we have to drop down into the 5f block, and we're going to pick up all 14 of those, which will give us 5f14. After lawrencium, we go back to the 6d block, and we're going to pick up all the remaining members, the other 9 members of the 6d block, and add those to our 1, and that brings us up to 6d10. And finally, we're going to wrap things up by going into the 7p block, and flerovium is the second element in the 7p block, which means we should end with 7p2. So we can check our math. We have 86 for radon, 2 more makes 88, 10 more makes 98, these 14 make it 112, and the last 2 bring us up to 114. When I first started teaching chemistry many years ago, the textbook I used had what I thought was a fairly interesting model for the atom, which they called the electron hotel. The author envisioned an atom being designed like a hotel, and in a hotel, of course, there are floors. In an atom, we have something similar. That's our energy levels. So I thought that was a pretty interesting analogy. I decided to take it a step further, however, because, of course, in a hotel, the floors are further subdivided. Each floor is separated into individual rooms. And as we learned a little earlier, the energy levels in the atom are subdivided into subshells. And as I mentioned, the advantage of this is it helps keep the electrons away from each other. Electrons have the same charge, so they repel one another. So the more we can keep them separated, the better. So we've broken them into individual energy levels, and then even separated the energy levels into subshells. However, according to quantum mechanics, we can go even further. Now, in the hotel analogy, if I said, how can we further segregate the guests in the hotel beyond the floor and the room? Well, perhaps which bed they're sleeping in. We have a similar type of thing in the atom. Each subshell in the atom is divided up into individual little units called orbitals. So an orbital is sort of like a bed. In fact, it's quite similar because normally in a bed you can sleep two people, and an orbital is the same way. In an orbital, you can only have a maximum of 2 electrons. The energy levels, we were able to figure out the number of electrons by just using 2n squared, and that would calculate how many electrons maximum could fit in the level. The subshells, we can simply count them. We start with 2 for the S, 6 for the P, 10 for the D, and so on. They continue to go up in increments of 4. And as I just mentioned a moment ago, orbitals always hold a maximum of 2 electrons. You can never have more than 2 in an orbital. You can have only 1, but it can never exceed 2. So what exactly do orbitals look like? The answer, of course, came once again from quantum mechanics and the mathematical equations of Erwin Schrödinger. Each orbital has a mathematical equation that describes it. And if you want to know what the orbital looks like, all you have to do is take a piece of graph paper and graph the mathematical equation. When they did that for an s orbital, it turned out that s orbitals look like a sphere. So simply graphing the variables in that equation, it determined that s orbitals were perfectly spherical. If you graph the equation for p orbitals, it turns out that they sort of look like a figure 8. It's almost like 2 balloons have been tied together. There are 3 p orbitals, and it's easy to figure that out, because if an orbital can hold 2 electrons and a p subshell holds a total of 6 electrons, we would need 3 orbitals. Each of these p orbitals can hold 2, and that gives us our total of 6. The way we separate those orbitals is the direction they point. So one is called the px orbital because it lies on the x-axis. There's a pz orbital, and there's a py orbital. Those 3 represent the 3 p orbitals, and that makes up the 6 electrons in energy, or in the p subshell. Now in chemistry 3A, this is usually as far as we go. There are d orbitals and f orbitals and even g and h orbitals, but normally in an introductory course this is as far as we get, but I thought it might be interesting to at least show you what the d orbitals look like. They're a little more complicated. You'll notice that most of the d orbitals have 4 segments to them. If we look back a moment, the p orbitals had 2 segments, and the s orbital only had 1. That trend continues. So s orbitals have a single component, p orbitals have 2, d orbitals for the most part have 4, and not surprisingly, if we did go as far as f orbitals, they would have 8. Some of the f orbitals look like 8 little balloons tied together. The d orbitals, most of them look like 4-leaf clovers. If you take general chemistry, if you go on to Chem 1A, you will learn all about d orbitals, but as far as Chem 3A is concerned, we are only going to deal with the s orbitals and the p orbitals. Now we can add a 4th component to our electron hotel model. If we really wanted to know precisely where a guest was in the hotel, we'd want to know what floor they're on, which room they're in, which bed they're sleeping in, and to be very specific, which side of the bed they're on. In the atom, there's a similar type of thing. It's called the spin of the electron. We can envision that the 2 electrons in an orbital spin in opposite directions. No 2 electrons can have exactly the same location. They can be in the same energy level, the same subshell. They can even share an orbital, But in the orbital, they have to have some way to differentiate between the two, and that differentiation is what direction they are spinning. The four measures, though, the energy level, the subshell, the orbital, and the spin, are known in chemistry and physics as the quantum numbers of that particular electron. Each electron has a set of 4 quantum numbers. Again, this is something that you're going to get into in general chemistry if you move on to Chem 1A, so I'm just briefly going to touch upon it here. But in general terms, the first quantum number tells us which energy level an electron is residing in. The second quantum number tells us the subshell. The third, which orbital. And the fourth tells us which direction the electron is spinning. Those 4 measures of the electron's location are sort of like the address on an envelope. If you mail something to someone, you basically need 4 things. You need their name, you need their street address, you need the city they're in, and you need the state they live in. If you want the mail to get there, you need each of those things. If you leave off Utah, you're in trouble. If you leave off the town or the street address, you're in trouble. So just like a person will have a street address, this is sort of like the street address of our electron. There are some practice problems in the worksheet, but let's go ahead and we'll add a few extra to that to make sure you have a good understanding of what we've been talking about so far. Let's start out with just a basic electronic configuration question like we did a little bit earlier. So meitnerium, which is element 109, will begin with radon. So that's our starting point. That'll take care of 86 of our electrons. After radon, we'll go down to the 7s block and we'll pick up both electrons in the 7s subshell. That will give us our 7s2. We'll then move into the 6d block where we'll pick up just the first member there. That will give us 6d1. Then we drop down into the 5f block and we're going to pick up the entire 5f block. So we'll pick up all 14 members of the 5f. Then we go back up to the 6d block and we need another 1, 2, 3, 4, 5, 6 more, which will bring our 5d up to a total, or sorry, 6d up to a total of 7. If we check our math, we have 86, 2 more makes 88, 7 more makes 95, and another 14 adds up to 109, and that is indeed the number of electrons in meitnerium. Next, let's consider an atom of gold. How many energy levels are there in a gold atom? And I asked this kind of question numerous times during the course of a semester, and many students continue to get it wrong because they just can't believe that it's infinite. All atoms contain an infinite number of energy levels. The number of steps on the atomic staircase goes on forever. Energy levels are simply empty containers in which you can place electrons, and according to quantum mechanics, there's an infinite number of them. How many subshells are there in an atom of gold? Well, if there are infinite energy levels, there would have to be infinite subshells, because there are clearly more subshells than there are energy levels. How about orbitals? How many of those are there? Well, of course, that's logically also got to be infinite, because there are more orbitals than there are subshells. And then finally, how many electrons are there in an atom of gold? Now, I hope you paused a moment before blurting out your answer, because the answer is not infinite. The number of electrons is fixed. It depends on what the atomic number of that element happens to be. You can have an infinite number of containers in which to place electrons, but no atom has infinite electrons. If you look at the periodic table, of course, we can see that an atom of gold actually has 79 electrons. So we're not using all of the energy levels, subshells, and orbitals available, only a tiny portion of those. All right, how many electrons can the 9th energy level hold? Doesn't matter what atom it is, it's the same for every element. If you remember, our little equation was simply 2n squared, where n was the level number, in this case 9. So if we take 2 times 9 squared, it turns out that that energy level can hold 162 electrons. Now, how many orbitals are there in the 9th energy level? Well, that's relatively easy. The best way to calculate the number of orbitals is to first figure out the number of electrons, and then remember that each orbital can hold 2 electrons, so the number of orbitals is simply the number of electrons divided by 2. So there are 81 orbitals in the 9th energy level. Each one can hold 2 electrons, thus are 162 electrons. How many subshells are there in the 9th energy level? That's a really easy one, because if you remember, the number of subshells is just whatever the level number is. So if you're in level number 9, there are 9 subshells. If you're in level number 347, there are 347 subshells. So you should be able to calculate the number of electrons and orbitals and subshells in any energy level. Again, it doesn't matter what the element is. It can be any element. They all have the same levels. They just have different numbers of electrons. This problem is an extension of one of the questions we had on the worksheet. In the worksheet, I asked you in which element is the 3rd energy level first completely filled, and a large portion of students tend to miss that question. So we're going to see if you learned anything from that to answer this question. To fill the 4th energy level, we need to fill all the components of the 4th energy level. Very commonly, what students will answer for this question is krypton. Say, well, krypton is at the end of the 4th period, so that must be the end of the 4th energy level. But that is absolutely not true. You have to ask yourself, what is the 4th energy level made of? Well, it contains 4 subshells, a 4s, a 4p, a 4d, and a 4f. In order to completely fill the 4th energy level, you have to fill all 4 of those subshells. The 4s subshell will be filled when we get to calcium. Potassium and calcium fill the 4s. For the 4p subshell, we have to fill the 4p block. So krypton is not at the end of the 4th energy level. It's only made it as far as the 4p. Keep in mind that the end of a period doesn't necessarily mean that's the end of an energy level, because we fill a lot of the subshells out of numerical order. To fill the 4d subshell, we have to fill the 4d block of elements, which takes us to cadmium. And finally, to fill that 4f subshell, we have to fill the 4f block of elements, and that takes us all the way to lutetium, element number 71. Quite a few students will get that answer correct in class. I always like to wrap up Chapter 11 with a challenging problem. And this one is pretty challenging. I ask it every semester, and in a good year, perhaps 1 out of 30 students will actually get it right. If you've learned anything from the previous problem, you should get it right. So let's see how we can figure this one out. Since we're in the 5th energy level, we have to fill all of the subshells in the 5th energy level. And what students tend to forget is that includes the 5G. We have to fill the S, P, D, F, and G subshells. Now, you'd be amazed at how often students will tell me, there's no such thing as a 5G subshell. And the answer, of course, is sure there is. There's every possible G subshell, because all energy levels exist, all subshells, and all orbitals. There's a 57 G subshell and a 342 H subshell. They're all out there. We just may not be using them all at the moment. To figure out when the fifth energy level is completely filled, we have to fill all 5 of these. So we'll begin, and we'll fill the 5s. That gets us to strontium. We'll fill the 5p. That takes us to xenon. The 5d gets us to mercury. And the 5f takes us to lawrencium. That is what I tell students is the #1 wrong answer. Most students will pick lawrencium as the answer to the question because they didn't think it through. We're not to the end of energy level number 5 yet. We have to go through the 5G subshell, and you probably noticed it's not on the periodic table for a very simple reason. The element that contains the 5G subshell simply hasn't been discovered yet. That's not going to happen until we've come up with a few more elements. We're only up to element number 118 yet on the current periodic tables. When we hit element 119, we're going to begin the 8th period, and when we get into the 120s, we will actually begin to fill the 5G subshell. Well, that wraps up everything for Chapter 11. So at the end of Chapter 2, we had finished discussing the basic structure of the atom. We did our cathode ray experiments and figured out the identity of protons, neutrons, and electrons. Now in Chapter 11, we have delved more deeply into the structure of the atom. We've determined that the electrons aren't just flying around everywhere in the atom. They are actually arranged very specifically around the nucleus into energy levels and subshells and orbitals. In Chapter 3, that we'll be starting next week, we're going to use this information to allow us to predict what different elements are going to do in chemical reactions. We'll talk about why for most elements the number of electrons that they currently have or that they start with is not the amount they would like to have. They're not as stable as they could be. In Chapter 3, we'll learn how atoms can give electrons to other elements or take them from other elements to get just that perfect number of electrons. And that will allow us to predict the chemical compounds that various elements are going to form. So let's go ahead and get started in Chapter 3.